Okay, good morning, folks. I'm Raphael Amorim. I'm coming from Brazil. I'm part of the Atlântico team that cooperates with HP. We developed some projects there. Particularly, I'm working on the OpenFlow controller with the HP networking team for quite some time, about 2 years right now. And Renato Aguiar is another developer. And both of us been working with the OpenFlow controller on Java in the HP platform, and this work was basically kind of a reflection. Both of us are Lua programmers since 2000, been working on Lua Eclipse and also eLua for quite some time with Dado Sutter, and we thought about let's kind of relax some time and develop a Lua controller to see the difference between the implementation that we had on Java. That is very complex and basically leads to many bureaucratic decisions. And let's see how it behaves on the Lua development. So I'll do a brief overview about OpenFlow and how OpenFlow works, and the LuaFlow approach to implement a controller, a little demo, and the next steps for this project. So basically, the current internet that we have is closer to innovations because we are basically we have an infrastructure problem. We have many switches from many vendors, different operating systems, and some different commands to configure the switches. So the software-defined networking approach to open this is basically adding a network operating system that is common to all switches, and you can run applications on top of it. And basically, when you see like this, the switch is simple packet-forward hardware about now. And there's an open interface to the hardware, and also at least one good operating system that could be extensible, possible open source. There's an alternative written Lua, and it's not in production yet, but it will be sooner. There's a well-defined open API for implementing your OpenFlow apps. But what is OpenFlow at all? So OpenFlow is an API, short story. Control how packets are forwarded and make deployable networks programmable, not just configurable. So you have the ability of define how your packets are going to be forwarded in the network. You have the ability of create your own organization and dividing your network in slices for services or just what you want. Makes innovation very easy because you can test your concepts and make any kind of idea that you have possible. In experimenter's perspective, the goal is you don't have to build your special test bed. You basically validate your whole experiments on deployed hardware with real traffic at full line speed. So you have the whole network to debug, and that's okay. So basically, you have the Ethernet switch. There's a control path all about routing and forwarding, and the data path there is responsible basically for input and output, the datagrams. OpenFlow acts on the control path, and there's this new entity called the OpenFlow controller that basically talks using the OpenFlow protocol over SSL or TCP, raw TCP. So there's the OpenFlow table abstraction that runs in the controller. In the switch, there's those parameters like MAC source, MAC destination, IP source and IP destination, TCP destination and source port, and an action to perform in the network. So you have this first host, 5.6.7.8, and you basically the controller informs the firmware and writes on the flow table a rule that says that if the IP destination is 5678 of this packet, particular packet, write on the port 1. So the package actually goes to the port 1 and the machine receives the packet. So let's see. So flow table entries are basically a rule. You have several parameters from different layers of the TCP stack or the network stack. You have actions that you could program, like forward packet to port, encapsulate, and forward to controller, drop a packet, send to normal processing pipeline, modify some field that you previously set. And there's also a stats parameter to get how many byte counters you have and make sure your controller is working okay. So doing this, you can write several examples like switching. It's basically layer 2 routing a MAC address destination to actual port. Flow switching, you can have many parameters. Firewall, basically dropping everything from one port. You can write down a routing using IP addresses, and also VLAN switching. You can also do that. So it's a very flexible way of controlling your switches. So let's see one of the usages. Dedicated OpenFlow network with one controller. So Alice wants to send a packet to Bob. So basically Alice starts sending the packet. So when it comes to the switch, all switches are pointing to the controller. So basically the switches are down that time. So it will basically ask the controller what I should do with this packet. So it will inform everything to all the parameters of that packet to the controller. The controller analyzes, send all rules, actions, and statistics to the OpenFlow switches, and basically the packet goes to Bob. So some experiment design decisions. You want to forward in logic, of course, so your whole logic is forward. You have this centralized versus distributed control. You have fine versus coarse grained rules. You have reactive versus proactive rule creation. And it's a very open research area right now, OpenFlow. You have many applications. We've been basically working on new approaches, new demos, new scenarios, and there are many research opportunities. So you have the ability of have one controller controlling many switches, or many controller controlling many switches, separate your network in different VLANs, each one with a dedicated service and a dedicated controller, so you have the ability of doing anything. You can flow routing or aggregate, so you can define like you have a service like video, and you want to use a certain amount of bandwidth for certain service, and you basically can aggregate all flows that come to the particular that match with the particular service with the same rule, and the switch will basically route that rule. Or you can treat per flow basis. It's not very common, but it's depending on the service that you're working on, you can use this. There's the reactive versus proactive. So you could respond as the flows come in, or you can also, if you know that in your network you currently have a certain service that runs 8 p.m. to 9 p.m. and you really need a deep and fast performance at that time, you can basically pre-program your network to that specific time. So you have the ability of detecting patterns in your network and basically reprogram your network to that pattern, those patterns. So some examples that we've been working on. VM migration across subnets to do some experiments with Elastic Cloud, identity-based QoS using .1x authentication. So one of the examples that we've been working with video streaming. So you have basically a demo that unfortunately we couldn't bring here. When you have two different laptops with video streaming, two different users logged in, and they basically get different performances because there are certain rules for that depending on the group or the user, you basically have different quality of services. So, and the switch and the network administrator doesn't really know about it, how the switches are being configured. He never get into the switches to configure anything. He basically sets I have those switches point to the controller. I'm creating this rule over here, and that's all. So the switches basically are self-awareness about this. Energy efficient data center network is also something very cool because during sometimes you have paths in the network that are not being used. Some machines are shut down, so the ports are not necessarily they are open, they are up, but they shouldn't. So you have a way of knowing that, optimizing your path to basically shut down every port that you're not using, every switch that will not be used, and basically you're going to be energy efficient in your data center. That's a very good scenario for energy efficiency. Network slicing, also good thing. Separate your network in different slices depending on the services that you have, or clients, or anything. And load balancing, it's also something that we're working on. DNS, load balancing. Basically, you have a service that you have a group of machines, like FTP server, for instance, or a video streaming service. And you basically, in the client, you say, I want to connect video streaming.hp.com. And the controller receives the secondary DNS request to solve to that particular subdomain. And it basically investigates the network, see what's the best route to the lowest load server, and basically returns the IP address of that server. And the client doesn't know anything about routing. The switches doesn't know, but the controller knows the state of the whole network. So it says, oh, this is the server for you. Get it. So we compare it with round-robin DNS servers, and basically it blows out the performance because you really have you're aware about the state of the network, and you basically have excellent usage of the network. So industry is embracing SDN. So there are many players that are working on it. Google recently said that they using in their infrastructure OpenFlow for the servers, and there are many players and also vendors like HP that we've been working on the ProCurve series switches. Those light credits, it's many people that work on the OpenFlow, and they speak about OpenFlow better than I. So this slide was also stolen. So the LuaFlow approach. So the official open source controllers are Nox. That is written in Python and C. There's a mixed approach both on enterprise code and testing and prototyping. Beacon is Java. It's basically focused on production environments. It's Java enterprise code, enterprise between quotes. So they're very complicated stuff. You have to read in and have several frameworks and stuff. So it's not quite good from one's perspective. And Trema, there's Ruby. It's basically focused on prototyping and testing, so you can validate your ideas right in your machine without having any infrastructure at all. So, very short, it's one principle, because we believe that there's a strong correlation between the length of the code, the number of tokens, and the programmer's productivity. And with smaller code, there are less chances of bugs and also less time to write consistent code. And I think Lua has made this excellent for us. So LuaFlow is specialized for programmers' productivity, but not compromising efficiency. Like a Trema, for instance, in Ruby, it's basically testing. You don't really want to do your production code with it. So why LuaFlow? So because we write C in Lua, and Nox is written in C++ and Python, Beacon is written in Java, that's the main reason. So we want to bet on Lua to see that, because we think that we could win both ways. So that's a sample of the configuration file. It's very straightforward. So if you want to do some tests with a test network, you could basically create your switches and hosts and set the connections. There's a little DSL to do configuration. So basically a connection to the host to the switch port 2, host switch port connection to the host 2, switch 2 on port 2, and switch port 1, switch 1 port 1 to switch 2 port 2. It's a linear topology, 2 hosts and 2 switches in between. So how does it go on the paper? So you have the traffic between the switches and the hosts are basically this. You have a packet. When the packet arrives to the switch, it generates a message, OpenFlow message called packet-in. It's sent to the controller. There are a bunch of information about that packet. So the controller at that moment has the ability of send a flow mod message to update the flow table, so you can persist the information on the flow table. So the next time a packet comes in, if it matches the configuration that you created, basically the switch will not bother the controller anymore. Basically, route for it all. Or you could also send a packet out to a specific port, so you're not lost the first packets of your connection, because basically the first packet will get into the controller will analyze. If I do nothing with it, basically the switch is waiting for this. What should I do with the first packet? So if you don't pack it out, basically you're lost. So if you start pinging, for instance, and basically the first ping response will be missing, and after that, basically the next packets will be okay. So basically, pack it in, flow mod to configure the switch, pack it out what you have, and that's okay. So we want to avoid this kind of thing that you have in Python. So the Nox controller, you have those 2 functions do the same thing, add a simple flow to the flow table. So, but Lua, you see, it's much more cleaner, and it was a bad design decision, because Python, you have classes and stuff, and I think it's kind of enterprise approach that does not fit for our needs. So you have to cat network events. You basically have a switch read message, so you can actually get all the features from the switches. Here we are listing all the switches that come in. They have a 64-bit ID. It's called DPID. That's in C right now, because we don't treat that in Lua code. It's in C code. And we basically listing all the properties in the ports and of the switch. So all the properties are there. You can also use this function to create your whole in-memory infrastructure of the network and topology, etc. Populating the port values, the bandwidth, the speed of the port, etc. You have the packet-in. You basically receive the data path ID, the buffer ID where you're going to write down your outputs, and the flow, and basically it's printing I received this new packet from this. It is written in this buffer and receiving from the switch. I'm setting the timeout to 10, and I'm forwarding to all ports in the switch. So it's basically a hub, and adding this rule to the switch. So we've written also some base classes to you guys playing with, like topology, port, host, switch. So some Dash implementation to calculate routes and stuff. So it's basically what we have. And that was some kind of experience, because when we started writing, we kind of in that mindset of Java mindset of creating this whole object infrastructure. So we started on by creating some getters and setters and stuff like that. And we realized that we really don't need that. It's all Java bureaucratic way of building stuff. And basically it's very bad language to use its whole data structures. So you basically can use hash maps or hash tables to build your abstractions, because it forces you to not use those data structures, and you basically keep creating new classes to represent your new objects. And we basically using tables inside tables and some meta table to add some mechanisms for object orientation to. But it's basically there are basically no extra methods, but very basic stuff, and we don't need extra methods to do that. You could do absolutely everything. So one example, using base classes, basically require topology, create a new topology with a name, and load the configuration for the configuration file. And you can insert your switch features into switch objects that you create, and basically create a route using some algorithm for them. It's very simple code. And you have your controller right there. So let's a short demo here. So the input and output is treated on C. So it's 652K, the executable. We have some examples here. So let me call LuaFlow. Let me show you guys the first. So I'm implementing a hub here. So basically the hub is logging in the switch properties. And basically it adds a simple flow to all ports and to the switch that come in. So basically you receive a request right out to all ports. So that's basically what it's doing. So I'm going to run this. I'm going to use Mininet. There's a network simulator to create the network for us, the hosts and the switches, and it will point to our controller. Okay, so if I try to, I have host 1 and host 2. If I try to ping host 2, it will basically fail. You can see that it was unable to contact the remote controller. So it fails. So I'm going to start the controller. Do a hub. So you're not paying attention in time for now. So he received some capabilities and some. So it's receiving packets, UDP packets right now, like ARP or other traffic. I'm going to ping right now, and it's okay. You notice that in the very first moment was a little extra time to forward, but that's okay. After that, the switch has fulfilled the full table, and there's no communication with the controller. So we just shut down everything, and let's see the second demo. So the hub basically forward to all ports. The second demo is a more complex one. It's a L2 switch that basically learns there's a L2 map to map switches to buffers, and so you can you know which switch has which port connected to which host, so you keep track of it, basically to do a routing, simple routing, and you will receive a new packet. We'll check if it's UDP traffic. If it's UDP, we're basically going to drop the flows, so you're not going to receive those messages like that UDP traffic that we are receiving in the very beginning of the execution of the controller. And if there is no out port, we basically flood, like ICMP. We basically flood because there is no destination port. It's basically broadcast. If it has a port, we're going to add a simple flow to the table saying, okay, forward this port to the destination. So when a host comes in, it will basically, the controller will receive the message, it will map. Okay, this host is in this port of this switch. This host is in this port of the switch, so it's mapped. So right now I can lead with any packet that comes in. So I'm going to start again. The mini-net controller. Just put this here. So what I'm going to do. So as we're treating with TCP traffic, I'm going to use iPerf. It's a traffic generator too. So I'm going to start iPerf as a server on host 2. So it's listening on the 50,001 port. 5001 port. I'm going to start the controller. And I'm going to fire an iPerf from host 1 to host 2. Okay. So it's connected to 10.002. Oops, yeah, that's okay. So he learned about, the switch learned about the port with each host is connected. And if we get back to the iPerf, it finally succeeded and transferred all the data from one path to another. So it basically, it's very simple to separate, classify your packets. If it's UDP or TCP, you have access to all information, and you can create your own rules to do that. So that's pretty much about it, the demo. So you have some extra features. Let me see here. So you have those. You have the base classes here. So basically, what I was talking about some base classes like base config and stuff. You can use. Very simple stuff. So you can basically, topology has name, nodes and links, and you can basically load the configuration. Get the route using Dijkstra. It's very simple code. Edge weight. You can add flows to the ports of the topology of each switch and classify the route, getting the route that has the majority of the free bandwidth. So it's very simple. You can modify as on your own. Very simple. So let's get back to the presentation. So next steps. We're writing a pure Lua controller using FFE, and LuaJIT also. Basically for testing, it's the new black, like was hit yesterday. More real-world scenarios to the community. We have plenty of scenarios in HP, but there are some NDA restrictions, so we're going to do different scenarios. That we don't had quite a time to do that, but we are going to provide, and also some ideas from the community, documentation, serious evaluation. So we're going to perform some tests comparing to enterprise controllers, and also there's a good opportunity to use OpenWRT, OpenFlow wireless devices. So you inserting wireless devices on the scenario is very cool, because you can basically your hosts are going to switching to different positions in the topology, and you basically will try to keep the path aligned at what you want and keeping the performance up and stuff like that. Also receive community pull requests, both IDs and code. There's the link to the initial repository. So in Bitbucket. A little piece of advice for you guys. So you heard yesterday Crazy Ivan plus 3D printer. I think that's self-replication probably. It's an attempt. Fabian's talk on machine-to-machine applications, self-awareness networks, Skynet. The fact is that we are in 2012, you've been warned. So thank you all. It's an honor to be here and meet you guys. And if you have any questions.
I noticed that you had a Dijkstra computation sort of engine in there. Have you done any work with relatively large topologies to get a sense of whether Lua is fast enough to do a Dijkstra computation?
Not yet, okay. But we are thinking about that. That's the serious performance. So we're going to do that. But in this very context that we are working on, this managing different slices of the network, that doesn't change at all, and also the routing is also basically the topology of the switches doesn't change at all. Those slices, basically the hosts are changing every time, but the topology is not. We're basically going to keep the route cache or stuff like that. But that's an idea to see that.
So I'm suggesting you're cheating, because in real networks the topology changes all the time, and I'm wondering if you've done work in like actually trying to do dynamic topology discovery, when links fail and are restored, and I guess it's sort of another case of looking at what. How much traffic or capacity is being used on the link. So if you're trying to do a constraint-based Dijkstra computation, to compute a path across the network, whether it's up or not is really, you might have zero capacity if it's not available.
Yeah, it's something that we work on HP. So there are currently some algorithms to do that. Actually, also there's a mechanism of you select different QE priority queues in the port, so you can balance the performance during the paths. You can select, okay, this flow come here in the first switch. You can select a lower priority to gain over there in a higher priority capacity in the next hopes. So that's something that we're going to working on in the open source project also, without interfering with the NEDA restrictions that we have today, because basically we're going to try to build with the community new algorithms, also thinking about that. Thank you. Any more questions?
Bom dia. Do you have, if I wanted to play with this and I wanted to not use Mininet and I wanted to actually get devices, what are some low-cost options, or are there any low-cost options?
I should probably tell you, buy some wireless devices, I think. With OpenWRT, I think you're going to be well with it. It's very cool to kid with your familiars, your parents, to avoid extra traffic in the network and basically redirect all to you, and something like that, using .1x authentication. You could play around it in home with that. I already did that, and my brother was furious about this, because basically he couldn't do anything because... Okay. Thank you, guys.